Hello and welcome to part 3 of the Learn pymatgen series. In this part, we'll talk about how to use pymatgen to get data from the materials project database. So this will allow you to find materials that meet certain property criteria. It will allow you to get their crystal structures, their band structures, their elastic tensors, and a whole bunch of other properties that you might be interested in. So let's just begin by talking about what is the materials project and its API. So the Materials Project is a database. It's a free database that's available to anyone, and it's been online for almost 15 years. And it contains lots of materials information that's typically from simulated data from density functional theory calculations. So as of this recording, the Materials Project contains quite a bit of information. It contains over 150,000 crystal structures. It contains over 70,000 electronic band structures. It contains, tens of thousands of elastic tensors, dielectric tensors, phonon band structures, etc. Now, before we begin, just a couple of optional notes to be aware of. The first one is that there are actually 2 Materials Project APIs as of this recording. The legacy API we're not really going to talk about at all in this tutorial. We'll talk exclusively about using the new Materials API. The second quick note is about how pymatgen exactly interacts with the API. Now, what pymatgen actually uses a library called MPAPI, a separate Python library that's maintained by the Materials Project team, and that actually does most of the work. So historically, pymatgen had an object called MPRester that was used to interact with the API. So that was in pymatgen.x.matproject.mprester. Nowadays, with the new API, it largely acts as a wrapper for the MPRester object in MPAPI. If that's confusing, don't worry about it. It's not really something that's important. The main thing that you need to know is that you do need to install MPAPI for the new pymatgen MPRester to work correctly. Okay, in terms of setting up for this whole procedure, there's just a couple of things that you need to do. The first one is you do need to get and set your API key. So getting your API key is pretty simple. You need to just go to the Materials Project. So here I'm going to the Materials Project, and in this section, if you click the API key, you will see your API key listed out as a long string. The next step is that you do have to install the MPAPI Python library. So if you just have pymatgen installed, you do have to install this library as well. The easiest way is to just pip install MPAPI. Okay, so with those 2 things, we can start to import MPRester and make sure everything works as intended. When you get your API key, you have 2 options. The first option is to actually configure your system so that your API key is always used when you call MPRester. That's using a command line called pmg-config. So detailed instructions on that is in this link. If you don't want to do the configuration of the API key, you can just skip this whole second portion of it, and you can just enter your API key directly when you import MPRester. So we'll show both options in the code example that follows. So regardless of whether you've set up your API key in the configuration file or not, we'll show you how to get everything imported correctly. All right, so here's the code snippet where we're going to just import MPRester and make sure everything is connected properly. If you've configured your API key using this command, you can just call MPRester without anything inside these parentheses. If you haven't done this configuration, you have to copy paste your API key string, that long string, into this code here, and then uncomment this portion of it. So then you can enter your API key manually if you haven't done the configuration. So if I run this code, it should import MPRester OK. And after doing that, it should also show that the type of this MPRester object is from mpapi.client.mprester. And that is what I have, so that means I properly installed the MPAPI library. Okay, so the first way we're going to talk about how to use the MPRester object is to use the built-in convenience functions. There's a lot of direct functions that just give you the data that you want, and all you have to do is to give it the material ID of the material that you want the data for. So you do need to know the material ID of the material that you're interested in to use these convenience functions. The easiest way to get those material IDs is to just browse the Materials Project website for the material that you want. So for example, you can go to Materials Project, and then in the Materials Explorer app, you can already see a list of materials and their materials IDs. And if you wanted to search on certain elements or certain properties, you can find materials that match those constraints and then grab the materials IDs of those. But once you have those materials IDs, you can come back and use these convenience functions. And later on in the tutorial, we'll also show how you can programmatically get the materials IDs by doing searches through the API, but that will come a little bit later. Okay, so the first thing that we're going to do is to use the convenience function, which is getStructure by material ID. So here I've grabbed the material ID for gallium arsenide, and if I just provide the material ID to this convenience function, it's going to give me a crystal structure. And if you saw part 1 of the tutorial, you'll be very familiar with these pymatgen structure objects. But here we've gotten the lattice and the basis and the atomic coordinates for gallium arsenide. And again, there's like 150,000 crystal structures at this moment in Materials Project. So there's a lot of different crystals that you can query using this method. The next convenience function that we'll cover is the band structure and density of states convenience functions. Again, if you just provide the materials ID, again of gallium arsenide in this case, you can get a pymatgen band structure object as well as a pymatgen density of states object. We briefly covered these objects in part 2 of the pymatgen tutorial. But anyway, if you just get these objects, one of the easiest things that you can do with it is to use pymatgen to plot the electronic band structure and DOS. So now that I have these objects, I can use the plotter. So here we go. I'm going to fetch the band structure, fetch the DOS, and then use the plotter to plot the band structure and the DOS. And this by default gives me an element projected band structure, which looks pretty nice. Okay, the next convenience function that we're going to use is the getPhonon band structure by material ID. And there's many fewer phonons currently available on Materials Project than electronic band structures. So here we're going to switch to cadmium telluride, which does have a phonon band structure in Materials Project. And so we're going to get this phonon band structure object, and then we're going to plot it with pymatgen. So by calling the convenience function, I was able to get the band structure object and then use the plotter in pymatgen to plot the phonon band structure. And this will tell me all the vibrational modes and their associated energies for cadmium telluride. Okay, and then the final convenience function we'll talk about is getting the Wulff shapes of materials, which basically tells you the three-dimensional shape that will lower your surface energy or minimize your surface energy. And that's currently just available for selected elements. So you can call the getWolffShape convenience function with one of the elements that are supported, and this will give you the Wulff shape object. And again, you can quickly plot this. And here is the calculated Wulff shape for lithium. So these convenience functions allow you to do a lot of things, but they don't let you do everything. And in particular, they don't let you search for materials that, get the materials IDs for the materials that you're interested in. So in order to really access the full power of the Materials Project API, you have to use SummaryResters. So these are attributes of MPRester that allow you to do other types of REST API calls. So the way that the SummaryResters work is that each SummaryRester is responsible for retrieving a particular type of data from the Materials Project. And it really works internally by interacting with one of the endpoints that are implemented in the Materials Project REST API. So we're not going to cover this in detail, but I do want to just quickly show you the list of endpoints. So those are documented in this link over here with accessing data. These are the different endpoints. I actually like this link a little bit better, so let's go here. And so here are the different endpoints that are supported, and different endpoints will give us different types of data and will allow us to perform different types of searches. So there's like a piezoelectric endpoint for getting piezoelectric properties. There is an XAS endpoint for getting X-ray absorption spectroscopy, etc. And if you expand one of these, you can see more about how this particular endpoint works. But getting back to the tutorial, there are various subresters of the MPRester. Again, these are attributes of the MPRester that is responsible for interacting with one of the endpoints in the Materials Project API service. So for instance, if you are interested in elastic tensor properties of materials, you probably want to use the ElasticityRester, which will allow you to search on elastic constant related properties, and it will return back that type of data back to you using the endpoint that's the elasticity endpoint in the REST API. If all this is confusing, I would just say don't worry about it. We'll go through a bunch of examples, but just keep in mind that there are many different subresters that allow you to interact with different parts of the Materials Project API. All right, so the first subrester that we'll cover is called a summary subrester. And this is probably the closest to like a one-stop shop in the sense that it allows you to search over a wide variety of materials properties. And it also returns back quite a lot of data for every material that matches. So I've kind of drawn a diagram of what the SummaryRester looks like, but it has a search method, and these are all the parameters of the search method. And these are all the things that you can search on when you use the SummaryRester. So you can search for materials with a particular density, or search for materials with a particular bulk modulus with the Royce averaging. And then the data that's returned to you is a summary doc for every material. And that summary doc is going to contain all of this information for every single material. And it's going to do this by interacting with the material/summary endpoint. So let's just show you an example of how it works. So we're going to first access the summary subrester that's in our materials project rester MPRester, .materials.summary. And so once we have the summary subrester, you can search on any one of these or any combination of these available fields. In this case, we're going to say we want materials that contain silicon and oxygen for sure. We want materials that do not have any calcium in it. We want materials that have 3 unique elements, exactly 3 unique elements. And we want materials that have a band gap between 0.5 and 1. So that's what this notation means, between 0.5 and 1. So if I run this, it's going to basically execute this query and find materials in the database that meet that criteria. And it found 36 materials that met that criteria. And if I print out the first result, so this is just the first result and there's 35 more of these, you can see that it returns the summary doc. And the summary doc is what I wrote here. And the summary doc is going to contain all of these different attributes. So it's going to contain, elements and composition. So the first material that matches is this barium silicate type material. And you can see that, all this information is there, including the band gap, which is between 0.5 and 1, just like we specified. This summary doc, if you want to access the information in it, it's pretty simple. You can just access the attributes of the summary doc directly, so things like the structure or the band gap. So it's pretty simple to get the results from the summary doc. So anything that's over here, you can basically just call using dot notation. Now, one side note about using the SummaryRester and all the different subresters is that you can be a lot more data efficient if you use this fields parameter. This fields parameter lets you not return the entire summary doc with all those different information for every single material. If you just want to know, for example, the band gap, the symmetry, and the composition of the materials that have your particular search, you can restrict the fields. So for example, this query will be much quicker, and it will just return composition, symmetry, material ID, and origins, the information that we asked for, and it will not bother looking up all this other stuff in the database, which will save a lot of time in the query and also result in a lot less data being transferred. The final thing to point out in this SummaryRester is this key called origins. Essentially, all the information that's in the SummaryRester for a particular material is based on many different calculations, combining the results from many different calculations. And if you want to know exactly which calculation was used, the ID of a calculation that was used to produce a certain result, the origins key is the thing that's supposed to contain that. And so if I call the origins attribute of my first entry, you can see that the structure came from a particular task ID. So this refers to one specific calculation that was used to generate the structure. And the energy is from another task ID. It's actually the same one. And the magnetic properties also came from this. So this task ID is actually the static calculation of a Vaspron, but other properties can come from other task IDs or other calculations. And this can be useful if you run calculations yourself, because as I'll show in the next part, you could use something called the TaskRester to look up the details of the calculation that was used to generate these properties. So the second subrester that I'll demonstrate is called the TaskRester, and this lets you look up the details of individual calculations. So the TaskRester, you can see, have different search parameters. There's only a few things you can search on, including the task IDs that we just looked up in the origins key. And the things that it returns is a task doc for the tasks that match, and the task doc contains different information than what we got from a summary doc. Tasks also has a custom function called getTrajectory, where if you give it a task ID, it will give you the full structure relaxation trajectory that show you all the forces and all the different structure snapshots along that trajectory. So again, this is for people that are really interested in the calculation details used to produce a particular result. And just to demo how it works, so again, this is that task ID from the origins key of the summary subrester that we just got. And if we search for that using the task subrester, so it's mpr.materials.task subrester, then we can get other types of information from the task doc that's returned. So we can get things like the input, the output, and also these calcs reverse keys. So I'm not going to go over these in detail, but I will run this. And just to show you that for this particular calculation, you can get things like the in-car parameters from the input parameters. And so you can see these are all like in-car tags. And if you saw the VASP tutorial from like part 2, some of these might look familiar. You can get things like output tags, output forces, output energies, etc. And then this calcs reversed key is going to have quite a lot of other information in it as well, which I'm not going to go through, but you can see, some of that printed out here. Okay, so the third and final subrester that we'll go over is called the ElasticityRester. And so there are many different subresters associated with the particular properties like dielectric rester and magnetism rester, etc. So I'll just demo one of them, which is the ElasticityRester. And this one really allows you to search over the mechanical elastic properties, things like the bulk modulus K, the shear modulus G, and the Poisson ratio, which is derived from these elastic tensors. And you can search for materials meeting certain criteria for these properties, and then the materials that match, you'll get back an elasticity doc for them. And the elasticity doc will contain more information about the elastic tensor than the summary doc did. So let's just take an example of how to use this. We're just going to give it a material ID and search on that. And so we see gallium arsenide, and we're going to basically search for the first results when we get gallium arsenide. And what we get back is a elasticity doc for gallium arsenide. And this elasticity doc will contain the keys that are here in the available fields. So it will contain more elastic tensor related properties like the elastic tensor, compliance tensor, bulk modulus, shear modulus, and like sound velocities derived from the bulk and shear modulus, for example. Like all the other MP data docs, like summary doc and task doc and elasticity doc, you can call individual attributes in order to access some of these properties. So you can call the .elastic tensor attribute to get the elastic tensor, .sound velocity to get the sound velocity, etc., etc. One thing to be careful of, though, is that the names of some of these aren't completely clear. So for example, you can get thermal elasticity, that thermal conductivity, and you might think that that's the thermal conductivity of the material that you search for, like gallium arsenide. But what this thermal conductivity key really is the glassy limit of thermal conductivity, which is a very lower limit of thermal conductivity if you have like lots of atom disorder. And it's not the crystalline gallium arsenide thermal conductivity. So you do have to be careful to know exactly what you're getting with some of these things, otherwise you might misinterpret them. Okay, so now that we've covered subresters in a little bit of detail, the next thing that I want to talk about is a more complicated topic, which is how to use multiple resters to accomplish what you want. Because many times no single rester is going to give you all the data that you want or allow you to search for all the fields that you want at once. So in that case, you have to actually combine results from multiple resters in order to get all the data or to be able to restrict on all the different fields. So I'm going to use an example where we want to search on both the band gap and we also want to search on the static dielectric constant. This is like a typical thing that somebody might want to do. And we also want detailed data on the band gap as well as on the dielectric constant, including its various contributions from ionic and electronic components. So there's no one rester that will allow me to do that. So I have to merge information from multiple subresters to do it. Okay, so the general procedure for doing this multi-step search kind of looks like this. The first thing I'm going to do is I'm going to search using one of the subresters. So in this case, I'm going to start with the SummaryRester, and I'm going to use that to restrict my band gap. I'll also add a couple of other restrictions in there as well, which we'll talk about. And then the materials that match, I'm going to store the band gap as well as any other information from the SummaryRester that I want inside a temporary database. It's going to be a dictionary. All right, so once I have the materials that match the first stage of my search, I'm going to move on to the second stage of my search. And I'm going to look for materials with material IDs that match the first stage of my search. So I'm going to pass the materials that matched, between the searches. And then I'm going to add the constraint on the total dielectric constant. And then once I have that result, I'm going to store the results from the second rester that I care about into a second dictionary. And then finally, what I'm going to do once I have both of these searches is to only restrict my data to the ones that match both of these filters. Because the second data actually already contains only data that matched my first rester and my second rester. But this first database contains data that only matched my first rester. It doesn't restrict myself to only things that match the dielectric constant search as well. So I'm going to have to just do a merge process that makes sure I only have materials IDs that match both of these. And if I had to do like a triple step or a quadruple step procedure, I could do that as well using this. So let's just get started. The first thing we're going to do is we're going to do the top half of this. So we're going to do these queries and we're going to store things in a database. So I'm going to start with my SummaryRester. I'm going to only look for materials that have dielectric properties calculated. That actually restricts us quite a bit because we only have a couple of thousand dielectric tensors calculated. So we can avoid too many queries by restricting ourselves to that. We're going to look for materials that have a band gap between 1.5 and 3. We want things that are oxides only, and then we want to store the material ID and the band gap because we're going to pass the material ID to the next stage of the search and we want to store the band gap for later. The next thing we're going to do is we're going to store this information into a dictionary. So we're going to store a dictionary of the material IDs that match this first stage of the search along with the data that we want to store, which is the band gap and the material ID. And then finally, we're going to get the material IDs that matched and pass that to the next stage of the search. So here's the next stage of the search where we're searching on the dielectric subrester, and we're only going to restrict ourselves to the material IDs that match the first stage of the search. And we're going to add this extra constraint that the dielectric constant needs to be between 5 and 10. And then we're going to store quite a bit of extra information about the dielectric constants for the materials that match. So then we're going to put all that data into a second dictionary that contains the material IDs that matched as well as all this other information that we've got from the second half of the search. And then we're going to store these material project IDs which matched both of these searches, the first search stacked on top of the second search. Okay, so let's run that, and that's the top half of this procedure. So I got everything that matched the band gap, I got everything that matched the total dielectric constant, and I've stored that into a database. Okay, the next thing I'm going to do is this merge process, because remember, this database over here contains things that match the first search, but it is not restricted to only the materials IDs that match the second search. So I'm going to just do a filter where I try to combine data from both of these databases and only use the material IDs that match both of the searches. So in order to combine the information, I'm going to invent a new data structure using name tuple. So I'm just going to call it materials data, and it's going to contain some summary data stuff and some dielectric data stuff. And so I'll loop over the materials that match both of my queries, which is my search to MPIDs. And I'm going to append into this container for materials data the stuff from the summary data, which is this dictionary over here, and the stuff from the dielectric data, which is this dictionary over here. So this final database is going to contain a summary attribute that's going to contain summary data attribute that's going to contain this stuff, and a dielectric data attribute that's going to contain this stuff. So let me run that, and we'll see that this all data thing has a total number of results of 367. So that's what matched both of the queries. And then if I want to get, for example, the band gap of the first result, I have to get that from the summary data portion of my materials data object, and that will give me the band gap. But if I want to get the dielectric constant, I have to get that from the dielectric data portion of my materials data. So if this is all a little bit confusing, I would just encourage you to look at it a couple of times or just take the code and fiddle with it a little bit. But then you'll kind of get the hang of how to do these multi-rester queries. Okay, the final topic I want to talk about is just how to be faster and more data efficient with the materials project. There's a lot of opportunities to just waste time and waste data transfer when using the Materials Project API. And so if you know how to be data efficient, you can get several advantages. The first thing is you'll just develop a lot quicker because you'll spend a lot less time waiting around for the Materials API to return you results. And it'll also use less memory on your side in order to do all the analysis. And then it's also good if you're data efficient from the Materials Project side because it just avoids a lot of unnecessary data transfer costs that the Materials Project has to be responsible for when they ship over large data sets. So some of the tips in order to minimize your data transfer. The first one is to use that fields attribute that we talked about before, the fields parameter that we talked about before, where we only get the data that we really care about. So we only get like the materials ID, the volume, and the elements or something like that, and we don't get that entire summary document that contained a ton of information. The other thing that is not really documented well right now is that if you're just exploring and testing things out and you want to just like not wait for thousands of results, you can use the num chunks and the chunk size parameters when calling search. So for example, if I just want to see how things are working and I want to have this band gap between 0 and 10 query, this would result in like tens of thousands of data points, and that's going to take like a lot of time to transfer over. So if I set num chunks to 1 and a chunk size of 10, it's only going to return me 10 results, so one chunk of 10 results, and that's going to be really, really fast. And so this will allow me to just quickly, get up and running and get everything connected. And then when, everything is connected, maybe I'll take these limits away and then do the full search. The last kind of efficiency tip that I'll talk about is if you basically want to minimize the number of times you call the search function in the API. And so if you have a lot of materials IDs and you want to search for data on all of them, don't have like a for loop where you search once for every single material that you want data on. Instead, pass a list of materials IDs to the search function so that you call it once. And that's going to give you the results much, much more quickly, and it's also going to be more efficient on the Materials Project side. So there's actually a few other tips in this link over here, but I think those are 3 to get you started in being a bit more data efficient. All right, so that's the end of the tutorial for how to use the Materials Project API with pymatgen. Hopefully this gets you started in getting lots and lots of materials data for your analysis. And if you are interested in more details, there is documentation from the Materials Project team, which is linked over here. So that's it for today, and I will see you in the next video.